This is chapter 20 continued, so we're talking once again about percentages. Remember, in our first part we figured out how to find the expected value and standard error for percentages in a sample, as well as to find the specific chance for our percentages of interest. So now we're going to talk about the accuracy of a sample. So for example, 212, Brigham City has a population of about 49,000, while about 8.2 million people live in New York City. Okay, so Brigham City is small, New York City is huge. If we were to draw a sample of 2,000 from each of these populations and compute the expected percentage of senior citizens, which would we expect to be more accurate? So 2,000 people from the small town of Brigham City, or 2,000 people from the big town of New York City. Which one would you expect to be more accurate? So it turns out what we're going to read just a little bit further on is that they will actually be the same accuracy because the sample size is the same. So it turns out that as long as your population is much bigger than your sample, your population size doesn't actually affect our estimates. If you notice in all of the calculations, I never asked you what the population size was. All I cared about was the sample size. Okay, so let's underline that. Only the actual sample size affects our estimates. The absolute size of the sample, so just how big your sample is, if we have 2,000 people in Brigham, 2,000 people in New York, the absolute size is the only thing that determines your accuracy. The size of your sample relative to the size of your population doesn't matter. For an analogy, if you think that seems weird, is suppose you're taking a drop of liquid from a bottle for chemical analysis. If your liquid is well mixed, it doesn't matter how large the bottle is. So it doesn't matter if we take a drop from a cup or a drop from a gallon, we're going to get the same results as long as our liquid was well mixed. Or in other words, as long as we take a good sample, it doesn't matter if we're taking the sample from Brigham City or the sample from New York. The only thing that actually matters is the sample size. So for example, I'm interested in estimating the percentage of people who watch a particular news broadcast. In each case, will the Logan or Salt Lake sample give more accurate results, or would they be the same? And for your information, Salt Lake has about 191,000 people and Logan about 49,000 people. Okay, so Logan is small, Salt Lake is big. So number one, if we were to take a simple random sample of 500 Logan residents and a simple random sample of 500 Salt Lake residents, which sample would be more accurate? So in this case, we have the same sample size. They both have 500, so we have the same accuracy for both Logan and Salt Lake. Number two, a simple random sample of 5% of the residents of each city. So to do that, we need to figure out how big our actual samples would be. So for Brigham, it would be for Logan, it would be 5% of 49,000, which is 2,400 people, 2,450 people in the sample. But if we did 5% in Salt Lake, 5% of 191,000 is equal to 9,550. Okay, and so if we did that, then this one is a bigger sample size. Because 9,000 is bigger than 2,000, and so it would be more accurate. So that's just a short note about the size of your samples and accuracy. And now we're going to do another short note about sampling without replacement. So all of our procedures with box models and using the normal curve are assuming that we're drawing with replacement. So you take someone out and you put them back. However, when you're taking samples or surveying people, it doesn't make sense to survey the same person twice. There's just no point. It's a waste of time and money, and so it makes a lot more sense to sample without replacement. So anytime you're actually doing something with sampling or surveying, you're going to want to sample without replacement. You don't want to do the same person twice. Okay? And technically that means all of our computations are going to be just slightly off. But luckily, if your sample is small compared to your population, small sample compared to the population, it doesn't actually matter if you sample without replacement. Okay, because the difference in our calculations is so small that it doesn't really matter. It won't make a big difference to you. Now, just as a note, the book does talk about a procedure for handling this case when your sample isn't small compared to the population. They call it a correction factor. But we're not going to use this. Instead, we'll just assume that our sample is small compared to the population. And now we're just going to practice everything that we learned in Chapter 20. So for example, 214, 25% of college students own an automobile. If we take a random sample of 400 of these students, what is the chance that less than 200 own an automobile? So we're going to have our population percent equals 25%, since 25% of all the college students own the automobile. And we're going to take a random sample of 400, so my sample size equals 400. What's the chance? So chance, I know I'm going to have to use the normal curve, that less than 20%, so less than 20% own an automobile. So first, let's find the expected value and standard error of the sum. So the expected value is going to be equal to our population percent, which we said is 25%. The standard error for the percent is equal to the square root of our population percentage times 100 minus the population percentage divided by the sample size. This is going to be the square root of 25 times 100 minus 25 divided by 400, which equals 2.16%. Now, that's just the first part. Now let's actually find the chance that less than 20% own an automobile. So if you're looking for the chance, you have to standardize. So it's going to be the percentage minus the expected value of the percentage divided by the standard error of the percentage. So it's going to be 20% minus our expected 25 divided by the standard error of 2.16. So this gives me negative 2.31. And then if I was to draw the picture, here's my negative 2.31, and we want the chance that less than 20%, so I'm going to want the area to the left. Let's go to the normal table and look up negative 2.31. The closest is this negative 2.3, with the area to the left being 1.07%. So that's my final answer. So let's write our little interpretation of what all this means. So, in a sample of 400 students, we expect about 25%, give or take 2.16%, to own a car. And then I can go a little bit further. Let's say we're interested in the chance that less than 20% own a car. So we can say, we can find that percentage. We figured out that it's 1.07. So there's a 1.07% chance of getting a sample where less than 20% of students own a car. So once again, we expect to see about 25%, give or take about 2.16%. Now, if you were interested in less than 20%, that's over 5 away. That's a little more than 2 standard errors away. And this makes sense then that that's a really small percentage, a really small chance of being less than 20%. Okay, our next example is going to teach us a very important concept. So for example, 215, a town has 25,000 families, of whom 10% do not own a car. Find the expected value and standard error for the percentage in the sample who own no cars if the sample size is, and so we're going to do this for all the different sample sizes. First though, our population percent is 10%. That will be important for all the problems. So let's go through each problem and find the expected value and the standard error. So expected value of the percentage is the population percentage, which equals 10%. Maybe let's do all the expected values first. Okay, and my next one, the expected value is just equal to the population percentage, which would be 10%. So notice that no matter how big my sample size is, I'm expecting to get about 10%. And the expected value for 1250 is about 10%. Now let's find the standard error for each. So the standard error for percentage, once again, is equal to the population percent times 100 minus the population percent divided by the sample size. So the population percent stays the same for each of these, but the sample size is going to change. So this is going to be the square root of my 10 times 100 minus 10 over my sample size of 250, which gives me 1.89. Now let's do it for my next one. Once again, the only thing that's changing here is my sample size. So it's going to be 10 times 100 minus 10 divided by a sample size of 2,500. And that gives me 0.6. And my final one, for sample size of 12,500, that's going to be 10 times 100 minus 10 divided by 12,500. Which gives me 0.189. So what do you notice? Once again, our expected percentage stayed the same. It's just 10% for each. But the standard error, we went from 1.89 to 0.6 to 0.189. Notice our standard error got smaller as the sample size increased. And it turns out that this happens every single time because of the formula of the problem. Since you're dividing by the sample size, when you divide by bigger numbers, your final result gets smaller. And so a very important result in statistics says that as the sample size increases, the standard error of the percentage gets smaller. That's very important because it means that bigger sample sizes are more accurate. Now, we learned in chapter 19 that that does come with a caveat of if you have a bad sample, making a bigger sample size isn't going to make it any better. But as long as you're using proper sampling techniques, then bigger sample sizes will be more accurate. And again, we're just practicing now. So, example 216, in a population of 100,000 people, we know that 20,000 are minorities. I take a simple random sample of 400 people from this population. I really don't know why all of my examples have been 400. Let's just change that up. Let's make that, say, 600. Okay, so number one, what percentage of minorities do I expect to get in my sample, and then find a standard error for this percentage? Let's just start with our formula. So expected value for your percentage is equal to your population percentage. Let's see, they didn't tell me the population percentage, but I can calculate it. There's 20,000 that are minorities, a total of 100,000. So if you want to do a percentage, it's just your part divided by your total. So the population percentage is 20,000 divided by 100,000, which is 20%. So my population percentage is 20%. The standard error for my percentage is equal to the square root of your population percent times 100% minus the population percentage divided by the sample size. So this will be the square root of 20 times 100 minus 20 divided by my sample size. And notice we did a new sample size of 600 just because for some reason all my examples in this chapter had used 400. So we just picked a new sample size so you'd see a different sample size. This gives me 2.66. So let's just write ourselves a note of what this means. So in a sample of 600 people, I expect about 20% to be minorities. I'm likely to be off by about 2.66 or so. Now when I say I'm likely to be off by that much, I could be off by less, I could be off by more, but we're most likely to be within that 2.66. So number 2, would you be surprised to hear that I got 21% minorities in my sample? So I expected to be about 20%, so would you be surprised to hear that I got 21%? So remember the rules. Maybe we'll write them up here. So you're likely, or 68% of sample percentages are within the expected value of the percent plus or minus 1 times the standard error of the percent. Okay, so this is just like what we did with linear regression, if you remember. And 95% of sample percentages are within the expected value of the percentage plus or minus 2 times the standard error of the percent. So we see these numbers come up over and over again in this course that we're doing. So within one standard error, that's what we say how much you're likely to be off by. And again, you can be off by a bit less than that, by a bit more, but because 68% of the sample percentages are within that range, we say that you're likely to be off by that much. For the 95%, because 95% should be within 2 standard errors, we say, well, you're not very likely then to be more than 2 standard errors away, so we're only surprised if you're more than 2 standard errors away. So number 2, would you be surprised to hear that I got 21% of minorities within my sample? So let's actually check and see what this would be. So the expected value of your percentage plus or minus 2 times the standard error of the percentage. So our expected value was 20% plus or minus, and my standard error was 2.66. So 2 times 2.66%. Let's see what this would give me. So 20 minus 2 times 2.66. And we're at 14.68. Once again, at this point, you don't have to worry about changing your percentages to decimals, so 20% doesn't have to change to 0.2. The reason why is we took everything into account when we made these formulas so that you don't have to do it to make it easier for this class. So 14.68 to 25.32. So this is kind of my expected range. So 21% is inside the range. So, not surprised. Okay, would you be surprised to hear that I got 15%? Well, if that's my range, 15% is also inside the range. So I would not be surprised. I just barely realized that I messed up. The standard error for the percentage, when I did 20 times 100 minus 20 over 600, I got my answer and I forgot to take the square root. This should be the square root of 2.66, which gives me 1.63. So let's go through and fix that everywhere. So my standard error is now 1.63. So I'm only likely to be off by about 1.63 or so. And that's going to change my range down here. So it's going to be 2 plus or minus, or 20% plus or minus 2 times 1.63. So my new range is 16.74% to 23.26%. Okay, so let's check. 21% is still inside that range, so I would not be surprised. But 15% is not inside the range, it is outside the range. So I would be surprised. Okay, so once again, once I updated my standard error throughout that problem, some of my answers changed.